Before I begin, I'd like to acknowledge Brian Cheadle and Kit Coleman, who hired me back in 1984. Sadly, Kit's departed just over a week ago, 2 weeks ago. But Brian's here, so good to see you, Brian. I don't know whether to thank you or not. I've been here for 42 years now and never did get away. So maybe it was a good decision. I don't know. Who knows? So I'm going to talk to you today about my book that was published in December of 2025. This is it. There are 16 chapters, 640 pages. Pretty heavy. I'll pass it around for people to look through while I'm doing the presentation. If you're bored, you can have a look. What are you talking about? Oh, yeah, it's in chapter 3, something like that. And it's a textbook on the physics of materials. But don't let that scare you, because I'm not going to talk about too much technical stuff. I'm going to basically focus on anything I find amusing. And basically the talk will be mostly non-technical, but you can pass it around, have a look. I've only got the one copy because it's expensive. And they make me pay for them. So,
but the library has a copy.
The library has a copy and they pay for it. Thank you. So, as far as motivation is concerned, I thought I'd want to start telling you the reason I wrote the book. There's a time, I'm going to quote, there's a time in one's life when there is a critical mass of knowledge and experience that allows one to make, or to better understand a subject and make connections with one thinks that, I'm going to start again. There is a time in one's life, because I can't even read this, when there is a critical mass of knowledge and experience that allows one to better understand a subject and make connections that one thinks may not be obvious to others. Some of you may recognize the cartoon by Dilbert. I like reading Dilbert. His name, the cartoonist, was Scott Adams, and he's one of my favorite authors, together with Douglas Adams, who wrote Hitchhiker's Guide to the Galaxy. So there must be something about Adams that people like, or I certainly like it. So my intent is to be able to share what information, what knowledge I've gained over my career. Basically 45 years working in some different respects in the nuclear industry. I want to share that with other people. But the thing is, you never really know whether you're just stating the obvious, you know, whether you're giving some insight to people, or whether, yeah, I already know that. I'm just like this guy here on the cartoon. If I can get him, I'm going to use this cartoon here, who has a blinding flash of light because he's stated something and seen it that's obvious. So in writing the book, I wrestled with some difficult concepts. And it would often occur to me that, oh, I remember being lectured about something up to this extent, you know, on this subject, back when I studied physics at Bristol University. And it never made sense to me. You know, I never understood a lot of what was being told. But now I do. And often in writing this book, I have occasions where I say, oh, that's what they were talking about. Now I understand. And I think to myself, why didn't they just tell us at the time? Maybe they did, and I was just too dumb and ignorant to listen to them. But what I'm trying to do also with the book is then write it in such a way that a younger me can understand. So you don't have to go through all that scratching your head and not understanding what they're talking about. And at the same time, I'm hoping that young engineers and young scientists will also be able to understand what can be a very complex, difficult topic. So, if I do have some readers, if I do get engineers and scientists reading the book, the most important thing is that they have to be willing to learn something. Anyway, so in terms of people being willing to listen or willing to learn, I want to talk a little bit about the Dunning-Kruger effect. Many of you may be aware of this phenomenon. I know it as the Machiavelli-Schopenhauer effect, because Machiavelli was an Italian philosopher and Schopenhauer was a German philosopher. They were talking about exactly the same thing, but hundreds of years ago. Okay, so it's a principle relating competence with confidence. And if you did science at university, you very quickly learn that you know nothing. You know, you start your lectures and you very, very, very quickly say, okay, I've learned a little bit and I realized how much I don't know. And that's like a universal truth that applies to most science students. The rest of people, I don't know if they ever get to that point in time where they realize, I don't know anything. But the thing about it is you can learn. So, and you can, if you have a certain amount of humility, you can say, well, yeah, I understand that I don't know anything. And to my mind, there are, in my career, 42 years of working, 45 years close, of working in the nuclear field. In my mind, I've come across two types of people. There are the unreceptive people who you can't talk to, because they know everything. And they generally, I would put them in this category here. They have low competence, but lots of confidence. And there are people you can talk to. So to give you some examples of what I mean by this and why I think it's important when it comes to writing a book directed at both types of people. So about 20 years ago, I was working in Chalk River, and there was some announcement made, and there was some emails going around because one of the groups had made some measurements that were unusually high. The values were unusually high. So this was unexpected. And in the nuclear field, if you come across something that's unexpected, that generally raises the flag and people get very excited about it. So this was S99 reportable. That means the CNSC has to hear about it. So I could see this going on, and I picked up a little bit about what it was about. And so I fired an email off to the group, and I said, listen guys, you're saying this is an unexpected result, but based on my experience, it depends what you mean by unexpected. Depends where you took the sample. If it was from 1 meter from the inlet at 12 o'clock, it's totally what I would expect. You know, you should consider where you took the sample. Anyway, I got nothing, no response, nothing back. And then 2 years later, the manager of the group was in a manager's meeting, and he said, look what my guys have just discovered. They deserve a medal. And I said to him, why? They've just reinvented the wheel. They've just discovered what I told them 2 years ago. And he looked at me and he said, maybe you didn't explain it well enough. And my inner voice wanting to strangle him was saying, no, maybe they just weren't willing to listen. Like you, they weren't willing to listen. On a more recent occasion at Queen's, I was helping some student with his writing some papers. I was reviewing a paper he'd written. So he'd done some work on density functional theory. And that's a way to decide on the stability of certain phases, certain precipitates. But it's a theoretical study. And I looked at it and I said, oh, yeah, but there are two references you haven't included. Some very good experimental work, which doesn't quite agree with what you're saying. And his response to me, he said, oh, I don't think that's relevant. And the alarm bells are going off. I'm thinking, man, somebody needs a lesson in ethics. I got him to put the references in, but he did grudgingly and didn't make the connection. Didn't say, here's some work that doesn't agree with ours. He just said, here's a list of references that are relevant, and that's it. So it was kind of frustrating. On the more positive side, people who are willing to listen, again, about 20 years ago, 15, 20 years ago, we had a summer student. He was a student in engineering physics from the University of Toronto. And he was coming for the summer, he was going to work with the branch, and he was doing some measurements that would involve using an SEM and a TEM. And he came to my office just to introduce himself, and I talked to him, and I said, this nice, pleasant kid. And then I thought, well, okay, I think I maybe talk to him a little bit and explain a little bit about what we're doing. So I took him aside, and I told him why he was doing what he was doing. And I gave him a little bit of a tutorial, if you like, on this type of work that was ongoing on the branch. After 2 hours, he looked at me and said, wow, I've just learned more in the last 2 hours than I did in the whole semester at the University of Toronto. In the same vein, about 5 or 6 years ago, I went to Idaho National Laboratory at the behest of the Electric Power Research Institute. So they were doing some experiments in Idaho, and the last time that they'd done these experiments, they cocked it up. They made a mess of it, and EPRI, who was paying for it, were really mad with them. So now they got a new set of samples to work with, and they asked me, EPRI asked me to go and oversee what they were doing. So I did that. It's okay, we spent a week. And then at the end of the week, Friday morning, the head of the group, the chief scientist, if you like, pulled me aside and said, can you explain a few things about diffraction and defect analysis and this? And we spent the morning in his office talking about these things. Maybe 3 hours. Same thing. At the end of it all, he looked at me and said, wow, I've just learned more in 3 hours than I did in 3 years here at Idaho National Laboratories. If I had $1 for every time somebody said something like that to me, I'd have $3. So I mentioned that it'll be mostly not technical, but I have to do a little bit. And what I'm going to do here is I'm going to show you basically what I told the young student from the University of Toronto. This is the summary of what I told him that morning. Is this on there?
How many common methods necessary to understand the structure?
One of the increase the volume.
Is to think of the atoms as being hard spheres. Now, metal atoms bond together by donating their outer shell electrons or their valence electrons into a common pool, and this allows them to stick together.
Yeah, like that.
Now, once we have this bond system in place, then the next level of bonding has to do with minimizing the energy of the system. And that can be achieved by packing the atoms together with the shortest possible bond lengths. And in this case, it's a close-packed structure. And this is an example of a single layer of a close-packed structure. It has this distinctive hexagonal shape. So I'm now going to think about the three-dimensional structure. Let's put down a first layer. It's easier for me to use 3 atoms in this case. So I'll just use 3, because then I'm going to set the next layer on top. which is my close packed layer, and I'm going to set it like. Now, if I want to build up a three-dimensional structure, I can do it in two possible ways. I can either put the next layer of atoms on here, like that. And you'll notice this atom here is directly above this atom here. So we call this atom, this layer, an A layer, and we call this layer a B layer. This atom, which has the same position looking down on the plane as this atom, we would also call that an A layer, because the layer designation letter defines where the position of the atoms relative to the whole lattice. So we have this ABA, what's called ABA stacking. And that's common, or that defines what is a hexagonal close-packed metal, this ABA structure. Now, the atoms don't have to, the third layer of atoms doesn't have to sit like that. It can go like that, or sit in this position, which is just as stable. In that case, we have A, B, C stacking. So there are three different positions for the different layers. So what defines what now is a 30 centicubic crystal structure, what distinguishes this from a hexagonal close-packed structure is simply the position of that third layer. So this is hexagonal close-packed.
See the cube.
And this is 30 centicubic.
I'm fine to touch any of this now. Okay, so this is a summary of what I just showed in the video there, and essentially what I told the young man from the University of Toronto. And basically what it describes are two crystal systems that are the important crystal systems for materials that you'll get in a nuclear reactor. So for austenitic stainless steels and nickel alloys, they're face centicubic or cubic close packed structure. And the thing I passed around there, the one where you can see the cube structure, the red atoms denote the corners of the smallest unit that you can have for that crystal. That would describe the crystal. And the other main alloy that you'd have in a reactor, oh, this is working now. The other alloy is zirconium alloys. So those are two types of crystal. And there are 7 crystal classes and 14 Bravais lattices. And Bravais lattices are the smallest unit that you can have that will, you can translate and recreate the whole volume, the whole crystal. So it's the smallest collection of atoms that defines the crystals, what is a Bravais lattice. And we want to talk about 2 of them, and they're the 2 most important ones. So, as I said, they account for most of the materials used in nuclear reactors. That's the most interesting. And they're unique because they're basically described by simply this atom close packing. But there are other complications when it comes to bonding. The subshell, the subvalent shell electrons, the P and the D electrons do affect the structure to some extent. And you get different types of crystal, but in the case, for the sake of nuclear reactors, these are the 2 most important ones. So apart from ferritic steels, and this is a body centicubic structures, slightly different. They're all probably just a glob of ping pong balls to you, but they mean something to me. The body centicubic, which is used in just outside of the core. People would not use body centicubic materials, which is the ferritic steels, in a reactor, because they're made brittle by radiation. So, but they're strong, so they're used in piping, in pressure vessel piping, outside of the core. So the only thing you're going to get in the core, the main ones you're going to get in the core, are the close packed ones, the face centicubic and the hexagonal close pack. So one may then wonder, why do you study crystal structures? I mean, why would I be interested in other crystal structures? Well, I'm not really. I'm only interested in those two. But you have to study them as part of your training when you're learning about metal physics. And they can be a source of amusement. So I put together this cartoon to describe a situation which really happened, and it's when I was a student, and I was taking a course on physics of materials, it was called. And one day I was going for lunch with some fellow students, and one of the guys, he was really miserable, and he didn't like Bristol at all. And he said, and he actually said this literally, look at this place, look at these, I hate Bristol, look at this place, the buildings are so monolithic. So I kicked my brain into gear, and I'm thinking, monolithic, that sounds a lot like monoclinic. And monoclinic is a type of crystal. It's one of the 7 crystal classes. And I also thought that, well, the slab-like structure that you get for a building, a high-rise block of flats, for instance, is more monoclinic. So I said, oh, I don't know. They look more orthorhombic to me. Sorry, did I say orthorhombic or not? I think I may have misspoke there. Anyway, the other guys in the group were very happy. They laughed. He didn't. He wasn't very happy. He now had 2 things to hate in Bristol: the town and me. So, apologies, Sam. I'm going to make this quick. What is it about metals that makes them so interesting? One of them that we have to understand is the mechanisms of plastic deformation. So when it comes to the close-packed metals, the ones that are important for the reactor core, there are 3 main modes of deformation. And they're basically the atoms of the metals deform by a shear mechanism. So if I can demonstrate, I've got some ping pong balls here, and I'm going to demonstrate 3 modes of shear. So one of them is planar shear, and that's where I'll talk about dislocations in a minute, you pass dislocations across a certain plane. I make a cut in the surface here, and I move everything relative to that surface in any way I can. And then you displace one half of the crystal with respect to the other. So that's one mechanism. There's another mechanism, which is a bulk shear. When you do that, if I can show everybody, I don't know if everybody can see this, you shear every plane successively by the same amount, but just a little bit. So instead of going a lot, I'm moving each one just a little bit, like that, like that. And what I end up then is a twin. And you'll notice, or if you can, this is a mirror image of the bottom half. The top half of the crystal is a mirror image of the bottom half of the crystal. So that's what a twin deformation is. There's another one, which is my favorite, which is a martensitic transformation. In a martensitic transformation, you don't move every plane equally at once. You move every other plane by one step, by one partial dislocation. And that's, I demonstrate that here. If I move that plane, and then this plane, and then that plane, that's a martensitic shear. It's not as much as the twin shear. The interesting thing about the martensitic shears, I've changed the crystal structure. This is now a hexagonal close-packed material. So that is, if I reverse the martensitic transformation, that is a face-centered cubic. That's one of the types, one of the crystal types that we have. And then I go that way, I now have martensite. I know Brian's heard of martensite. Well, you grew up dealing with martensite. So martensite is a very common type of steel that one gets. I would say probably a lot of martensite in cars, I guess, Brian. Not so much. Ferritic, but okay. Well, cars are mostly with a ferritic steel, so you don't get austenitic unless it's a DeLorean. You wouldn't have to worry about this unless it was an austenitic stainless steel car. So, I just told you there about the deformation of metals. Just to name a quick example. How are the metals put together? I mean, they're not single crystals. They're often agglomerations of single crystals, something like this. So what you have is a regular array of atoms, and then another regular array of atoms, and another array, and they're all different orientations, and they're all stuck together by a grain boundary, as shown here. So this boundary, in fact, so the bonding between all of the atoms, even in the single crystal, is metallic bonding. So we don't have to worry about it falling apart. And it may look as if the grain boundary is weak because they're all kind of randomly distributed. The grain boundary is actually the strongest part of the metal. And the reason it's the strongest part of the metal is because the reason you can deform easily the crystal is because of the regularity arrangement of the atoms. And that is because of a process called dislocation slip. We'll be through this in a minute, and I promise. So, who's had their elbow dislocated before? Nobody. Has anybody had anything dislocated? Oh yeah, there you go. Anyway, if you, but I'm sure you all know what a dislocation in the medical sense is. It's displacement of a bone out of the place where it should normally be. So you displaced it. So in the same way, in metal physics, a dislocation in a metal is the displacement of a layer of atoms, in this case here, out of their position. They're normally in some nice regular alignment here, all nicely lined up, and now we've got, I'm stuck, I'm in a different place, I don't have, my environment's changed. And if you can look at this, I mean, you've got a line of atoms here, so there's a line of atoms at this point in the crystal that goes down and into the board here, and it's called a line defect. So why is that? How does that relate to the deformation? Well, that's how metals deform. Is through the motion of dislocations. It's the mechanism. So if I start with a block of metal and I consider this line of sort of atoms, you know, something like this, and we start with a perfect crystal. And let's push on the crystal on the top half. And what happens is I break a bond. I break this bond here, and I make a new bond with this atom here between this one, and then I push that atom here into this dislocated spot. So it's out of place. But this top half, the crystal, has now moved a little bit along this line. And if I keep pushing, I can move that line further and further and further and further over until eventually it pops out the other side and you've got a permanent plastic deformation. What I put on here is something which is commonly used as an analogy to help explain, for the biologists amongst us, something that is physical in terms of metals, but in terms of a biological process. So those of you who are familiar with caterpillars, you'll know that they don't have legs. They have what's called prolegs. They're kind of like legs, but they're fleshy suckers that just stick to the ground, and that stops the caterpillar sliding around. And here's the caterpillar sat on its prolegs. It's got a highly segmented body, and how it moves isn't by moving around on its legs. what it does, it lifts its abdomen with a peristaltic motion, biperistaltic, by varying the pressure inside its abdomen. It lifts the abdomen, that drags its back end forward a little bit, and then it can ripple this abdomen along the length of its body until it pops out the end. So it's far easier to move than to drag everything across all in one go. If you do it a little bit at a time, then it's easier to make that motion. And that's how dislocations operate. And that's why crystals, as opposed to boundaries, which just seem random atoms, but they're still they're still bonded. That's why they're softer. It's easier to deform them. So another analogy include moving a piece of carpet. Who's laid a piece of carpet and, oh man, I'm an inch too short on this end, and it's riding up the wall on this end, and I can't drag the whole thing across. But what you can do is you create a ripple at one side, and you move that ripple across, and eventually, just like you have here, you can shift the carpet just with this gradual process. Another similar thing, but not exactly the same, is how many people have torn a telephone book in half? Not often? Well, you've probably seen it on TV, some strong man. Well, there's a trick to it, and what they do is that they shear the book. And that means that they don't tell you, but then they can, I can't do it. But when they shear the book over, like that, they can tear it a bit at a time, and then they go through the whole book. And everybody's going, wow, it's so strong, it's so strong. It's a cheat, it's a cheat. So that's line defects. There are another type of defect which is important, and I'm almost done with the technical stuff now. There are other types of defects which are important for the reactor. And these are defects that are produced by the radiation. So everything up until now I've talked about is not radiation, it's mechanical. But in a reactor, there are a lot of neutrons flying around. And these components have to do their job. They have to stay in place, they have to act strong and tough and last for 30 years, if not longer. But they're being bombarded by neutrons all the time. And to give you an example, kind of in a weak neutron environment, which is in the Candy reactor, in the pressure tube in the Candy reactor, you all know what a Candy reactor is, because we live so close to the industry. Tom doesn't. There's this Canadian reactor, and I'm going to talk about it later. Anyway, it's a very good reactor. Stephen once described it to me. He said it's engineered so well, it's like a Swiss watch. And it's engineered so well that it can run on dirt, basically, because you don't enrich the uranium. So Candy reactor is an amazing reactor. But you don't have as many neutrons floating around. But even then, every atom is displaced once a year. In some cases, you get more than that. So you've got these fast neutrons, and the bonds between the atoms, the energy needed to break the bonds, is typically anything between 20 and 60 electron volts. That doesn't mean much to you. Just think about 20 and 60. Relative to that, a neutron with an energy of a million electron volts is whipping through this material and bashing into these atoms. There's a difference in mass, so it doesn't transfer all of its energy all at once. It can transfer some energy, depending on the momentum transfer and the cross-section and the probability. But you can well imagine that when you've got high energy neutrons flying through the material, a lot of atoms are getting displaced. And when the atoms are displaced, that's these black things, they leave holes behind. And these holes are what's called vacancies. The collective, the interstitial atoms, the displaced atoms and the vacancies are called point defects. And they can move by solid state diffusion and cluster in different places. And this then has an impact on the properties of the material. It can make it weaker, it can make it stronger, it can certainly make it more brittle. So, in terms of a 1 MeV neutron, typically it'll create what's called a collision cascade. It'll go pow, and you displace all these atoms all at once. And you might get 400, 500, 600 atoms displaced just from one event. But there is a whole range of energies of neutrons in the reactor, going down to thermal neutrons. So you need the thermal neutrons to maintain an efficient reaction. And the thermal neutrons are typically a fraction of an electron volt. So you need 40 eV, say, to displace an atom. But a thermal neutron only has a fraction of an eV, but it can still displace the atoms. And it does that by being absorbed by the atom. Thermal neutron comes in, it gets absorbed by an atom, and that atom will emit a gamma ray, a gamma photon. The gamma photon has a certain amount of energy, and the relativistic mass of that energy is sufficient that there can be a kickback when you kick out that photon. It's just like light, but it's almost getting into relativistic. It is relativistic, in fact, because it's the relativistic mass which determines what kind of momentum transfer you have. So there's a recoil. And that recoiled atom can displace other atoms, but not many, maybe 4 or 5, something like that. Where it gets interesting, and where it becomes very important, is if you have a different type of element. And one element which is very unique is nickel. Coins are made of nickel. I think they are, aren't they?
Yeah.
No?
Yes.
Yes, yeah. I don't know if it's pure nickel or an alloy or whatever. But nickel is extremely unique when it comes to neutrons and radiation damage. The most abundant isotope in nickel is nickel 58. And nickel 58 will absorb a thermal neutron. And then it becomes nickel 59. Nickel 59 is amazing because it has a very, very high cross-section to absorb all kinds of neutrons. And the reactions that occur produce these emitted particles, not only gamma photons, but protons, which is like a hydrogen nucleus, and helium atoms, alpha particles, which are a helium nucleus. So not only does that then really enhance the amount of displacements, it enhances the amount of damage you get, but it also deposits a whole bunch of gases in the metal. And these gases, helium in particular, are very harmful to the material. Helium is bad. I'll finish my talk talking about helium, but it's basically something you don't want. So if you have helium and hydrogen production, it's not good. The good news is zirconium, which is most of the reactor core in the CANDU reactor. Zirconium doesn't form helium. There is some very, very, very high energy neutrons which can form a little bit, but basically it doesn't form helium. And for that reason, zirconium is very good. It doesn't swell like steels and everything else. It's a good thing to have. So not only do we have the fact that, I'll talk about zirconium in a minute. Okay, so these interstitial vacancy point defects, they migrate and they form clusters. They'll gather together to minimize their energy, and these clusters will jam themselves in between the planes and harden the material. And this changes the microstructure. So that's just like your bones in your body, that's the structure of your body. There are the structure, microstructure in a metal, which consists of dislocations, which you can think of as bones if you want. And we study the microstructure and the changes in the microstructure with various tools. So we have various tools at our disposal. My favorite is the electron microscope. Here's a picture of an early microscope. This is an optical microscope. So it's not perfect because it's not a transformation electron microscope. So to look at the innards of a metal, you need to shine light through it, or shine electrons, or shine something through it. So this guy, I mean, he's using an optical reflection technique to prove that it's a mammoth, but if it was the equivalent of what I need to do, or what me and my colleagues need to do, we have to shine something from the bottom and shine it out through this little tube to be able to see what the mammoth is made of, or its internal structure. Here's an early transmission electron microscope. Goes back 40 years. This is in building 375, metallurgical engineering branch under Brian Cheadle. And that's, do you recognize the guy?
Who is that?
No, he's no grey head. Anyway, so this is B 40 years ago in the lab. Electron microscopes are great for playing around. You know, you can use all the different physics principles that apply, in this case electron diffraction, and produce patterns, pretty patterns. This is a Tanaka pattern. This is a straight diffraction pattern of looking down particular axes of a crystal. It's like I'm looking down that way and to produce this diffraction pattern. Great if you want to design wallpaper, but not very practical. So what are we doing? For the most part, we use the electron microscope to look at structures inside materials, the structures that affect the properties of the material. This is actually a titanium, it's neutron radiated titanium. This is a picture taken on an EM200B at Whiteshell Laboratories. It's back in 1981 and 1983. I did some tours of duty at Whiteshell, which was great. I thought, I like Whiteshell, it's great. Chalk River can only be better, so when they offered me a job, when Brian offered me a job, I thought, oh, it has to be better than Whiteshell. There's a kind of, it's mix and match. I think there's some aspects of Whiteshell which I found I liked, some aspects of Chalk River I like. Not that I'm judging anybody. So these things that you see here, which look like ellipses, what you're actually looking at is like a layer of defects, like this. You're not looking at an edge on, you look at them like that. So that's why they have that appearance. Schematically, it looks more like this, and just to illustrate the principle of what I was talking about, you can either collect together a bunch of holes, the holes left behind, and that creates a vacancy loop, and when they cluster on a certain plane, they'll give a contraction perpendicular to the plane. Everything goes. And if it's interstitials, then like this, you'll get an expansion of the plane. So another microscope that's useful is a high voltage microscope. So if you want to look through a thicker piece of metal, you can just simply beef up your accelerating voltage. So in the pictures I showed earlier, the accelerating voltage was like 100 or 200, 1,000 electron volts. What that means is you have to have an accelerating potential of 100 kilovolts or 200 kilovolts. This thing I'm standing, this is me by the way. I'm standing outside of now is a 1 million electron volt microscope. And that allows us to look through thicker specimens. Not only that, 1 million electron volts is enough to beat the crap out of the atoms, so you can create damage at the same time that you're observing them. So when I was working here at Chalk River, one of my colleagues at Whiteshell, he wanted to do a particular experiment. He asked me to go to Stuttgart. This is Stuttgart, by the way. Oh, and by the way, there are, I guess I could try using this. There's another 2 stories above this, which is just the high voltage tanks to accelerate the electrons. So here's me, stood outside the high voltage microscope. This is the front panel, this is the back panel. Many years ago, I've forgotten how long ago it is now, in the 90s. So I used to go there, I had a young family, I'd fly overnight, Sunday night, get there Monday morning, I'd work, set up an experiment, carrying on till 2, 3, 4 o'clock the next morning, go home, go to bed, start again, 10 o'clock, and I'd work through the night like that. Once I went there, and it was a holiday, and the guy who was looking after me said, oh, so don't worry, Malcolm, we'll come in and open the lab. So he came in with his wife, and they opened the lab, and I said, oh, thank you, you've helped me, I can continue doing my experiments. Let me take you for lunch. I took him for lunch. And then she's whispering in his ear. And I said, what's she saying? And she doesn't understand how you can do this, how you can work day and night, like basically 16 hours a day. And you're here at lunch and you're joking with us and you seem to be okay. And I said, you don't have children, do you? I said, no. You will understand. You get used to not having any sleep at all when kids are around. I didn't mind going to Stuttgart. It was a very boring city, frankly. Bristol I love. I didn't know what that other guy was talking about, but Stuttgart I could leave alone. The one good thing about it is, oh, I should have put this on earlier. The one good thing about it is in this particular institute, the Max Planck Institute in Stuttgart, I could set my experiment up, and it might be in irradiation, it might take 7 or 8 hours. I could set it up, and then I'd be sitting around, it might be 1 o'clock in the morning, 2 o'clock in the morning. Oh, I think I'll have a beer. Down in the basement, there was a beer machine. You just put a couple of Deutschmarks in, grab a beer, and come back up, sit down, and oh yeah, and watch the microscope like a hawk, and maybe 2 hours later go and have another beer, Anyway, so it was a very pleasant way to do experiments. And here's an example of one of those experiments. So this is a video I took at Stuttgart. Some go to 3 o'clock in the morning or something like that, where I'm irradiating what's called a dislocation loop. And I'm irradiating a plane of point defects. So I'm irradiating with electrons with enough energy to displace other atoms. And then the holes left behind and the atoms can then interact with this loop. And the guy who wanted me to do the experiment, Chung Wu, he was curious to know which ones were mobile. And you can find out which ones are mobile by seeing what happens to the loop when you irradiate it. And if it grows, then the vacancies are mobile, and they're absorbing vacancies. Because I'd already previously analyzed this. Long job, actually. I got the neutron irradiated sample, did all the analysis here, shipped it over to Stuttgart, put it into the microscope, and then re-irradiated it. And this is a little clip of one of those irradiations. So here I am, irradiating this sample to see what happens to the loop. You have to understand something here. The sample is buckling and it's tilting and the beam is shifting and everything's changing. And the best way I could describe what it's like to conduct this kind of experiment It's like riding a bike and juggling at the same time, because the foot switch, you have foot switches to do the tilting, and then you have other hand switches to do the translation, and then you're trying to keep the beam on the same spot. And it's tricky. If you ask me now, oh Malcolm, will you go and do that experiment? Oh no, I couldn't possibly imagine it because it's just too draining. But when you're young, you can do that. Anyway, not just dislocations, you don't just look at dislocations. There are other aspects of radiation damage that's quite interesting. And one of them is a phase transformation. So this is a picture of a precipitate in a zircon sample. And it's been irradiated. And what happens, it's a very interesting phenomenon, is that the ion of this precipitate is diffusing out of the material. And when it's diffused out of the material is less stable. And it just basically transforms into an amorphous structure. It just goes, bleh, I've lost my crystal structure. It's like me smashing these balls and just scattering them. Not very practical use for this. And I must admit, I have to say that the very first person in the world who ever saw this kind of thing in an irradiated sample from in this case it was Peter Young, it was a guy called Ross Gilbert. In 1983, he did this work. It was just internal, it was only just discovered. And there was a couple of guys from GE visiting, and they got very excited about it, rushed off back to their lab, asked Ross Gilbert to send them all the details, which he did, but he thought, this is a bit, his spidey senses were up a little bit, and he was worried that they might try and publish the work, which is what the little assholes did. But fortunately, Ross, and this was just about the time when I arrived, he kind of suspected that, so he wanted to get a paper out quickly, and he did. And I was a reviewer on their paper when they submitted it. Like the journals, they said, please review this. And I said, you haven't referenced Ross Gilbert, And then they said, we don't know who he is, And yeah, they knew who he was. Anyway, I said, well, here it is. And it was published. Ross had got it in 1985, and that paper was in 1986. So when they had to reference it, because I'm a referee, and I say, you have to reference this work, they put it as 1986, hoping people would not notice. Because they were claiming that they were the first people to do it. It was pretty bad. Brian's aware of this. Anyway, another group that was very excited about this phenomenon, God alone knows why, I mean, a very little practical importance, was a group in France, at the Centre d'études nucléaires in Grenoble. They loved it. They did a lot of work. They had a whole group of people devoted to looking at amorphous transformations. In 2006, I was asked to go to a retirement function for one of the senior people at CENG who was retiring. And his name was Clément Emmanuel. This was in Paris. They paid, and I went, happy to go. And we were asked to make presentations which were in support of his working life. So I put in my presentation, and numerous things were in the presentation, but this one slide I put together, which basically related to the amorphous transformation, because that's what he was interested in. I said, okay, we'll do this. And this video, I'm showing you a video here of an amorphous precipitate from a Clandry tube, Nuclear Reactor Clandry tube. And what I'm doing saying, well, now it's the M13 globular cluster. But when you focus right in, you can't tell any difference. I think that's been finished, I think. I don't know why that would be. Yeah, I'm going to quickly, sorry we had those hiccups at the beginning, so I'm running 5 or 10 minutes behind. Does anybody have to get home at 8 o'clock? Can you stay another 10 minutes? Yeah, thank you. Anyway, so one of the things that's always tickled me about microscopy, electron microscopy, is you're delving into the infinitesimal. Your length scales are tiny, tiny, tiny. You're the size of atoms, smaller than atoms in some cases. And in comparison to that, you've got astronomy, which is infinite length scales. But they have a lot of similarities. And even the instrument, the telescope and the microscope, they're very similar. I like both. Get on to some more practical stuff. You can use the microscope to look at the internal structure. Let's forget the Morse transformations. Let's look at a Calandria tube, and this is a Calandria tube, typical Nuclear Reactor Calandria tube. And there's a pressure tube. Picture of a pressure tube. Is this showing up in here? Oh no, it isn't.
No.
Oh man. This is the I didn't realize I'm using the mouse now and you can't see it. Naomi, we have to talk about this at some point. I'm not coming back. Anyway.
We'll fix it.
This isn't your fault, it's probably my fault. I don't know, we'll have to do a post-mortem. What the hell happened there? Anyway, here's a pressure tube sample, and this is a Calandria tube. That's a twin, by the way. You'll notice all these little dark lines. And if you remember, I was talking about dislocations. What a dislocation was, it's something where the atom shouldn't be. It's a dislocation in the structure. Now, these provide all the strengths to the material. So pressure tube is very strong. It has to be strong to hold the system pressure in a reactor, and also subject to radiation and everything else that's going on. So it has to be cold worked, and Brian did a lot of work developing these tubes. Thank you, Brian. And one of the things was to cold work them sufficiently that they had enough strength. So if you look at the bottom here, the dislocation density here on the Calandria tube is very low. That's a 10 to the 12. What does that mean? I don't know. And this one, it's 4 times 10 to the 14. And you're thinking, well, what does that mean? Well, that's the length in meters per cubic meter of this material. So what does that mean? Here's a cubic centimeter of pressure tube. This is a sample, it's a tensile sample, it's a pure contact tension sample. If I took all the dislocations that you see here, and I strung them out, joined them end to end, I strung them out from this little bit of metal here, we could stretch them from the Earth to the Moon. If we took a full pressure tube, which is a 6 meter long tube, and there's 380 of them in a Calandria reactor, and if I took one pressure tube and took all those dislocations and stretched them out the line, we could stretch the dislocations from here to Pluto and back twice. So that just gives you an idea on the infinitesimal scale. We're still talking about enormous numbers, enormous lengths of this tiny, tiny structure packed in a little tiny piece of metal. Home track now, Naomi. So I mentioned about zirconium alloys, chapter 14 of the book, chapter 14, 15, 16 of the book, I talk about materials issues in various reactors. And in chapter 14, I talk about materials issues in heavy water reactors. Calandria reactor, Tusha reactor. But in the Calandria reactor, this is an example of this is the Calandria reactor. And it has all sorts of problems, issues that I'm summarizing and I talk about it in the book. The thing I put this up here for now is to repeat what I just said earlier. CANDU reactor is based mostly of zirconium alloys. And the reason it's made mostly of zirconium alloys is because zirconium doesn't absorb thermal neutrons. And the reason you want the zirconium alloys is because neutron economy is very important. Because the fuel in a CANDU reactor is not enriched. It's fuel, it's just dirt you dig out of the ground. So by the design, as Stephen once told me, by design, the CANDU reactor is designed not only in terms of the mechanical shape and the spacing between the channels and that, but also in terms of the alloys that make it up. But zirconium alloys are great if you want to have neutron economy, but they're not good for certain specialist components. And in this particular case, it's springs. Zirconium alloys are not very good for spring material. So what has been used in the past is Inconel. So Inconel X750 in particular is the alloy of choice that's being used in many fuel channels in the CANDU reactor. And this is a picture here showing how these springs sit on the pressure tube. This is the pressure tube and this is the spring. It's also known as the garter spring or a spacer. So these spacers, these garter springs, they act like garters, separate the pressure tube here, which is hot, from the climate tube, which is cold. They have to stay in place and they have to stay intact, so you can't have them falling apart. You can't have them moving because you don't want a big span of the pressure tube, and you don't want the pressure tube to sag and contact the climate tube. If it did that, it would form a blister and eventually it would go bang, as it did in 1983 and in 1986. So imagine the consternation. In fact, there was no consternation 15 years ago when they pulled some of these spacers out and they were broken. You know, and this was after 15 years of service. So this is a spacer that got shipped to Chalk River. So I was curious about this because I'm thinking, oh, well, that shouldn't happen. And this looks like it's an irradiation effect. The material is embrittled because it's being subject to radiation. And I knew that because I dealt a lot with Americans and Russians and Indians and whoever, the French. And I knew that this was a common phenomenon observed in other reactors throughout the world. But for whatever reason, there was a lot of resistance to getting worried about it. Senior management here at Chalk River, and certainly most of the engineers at Sherwood Park said, oh, that just happened because of the things got bashed around when they were in transit. I'm shaking my head going, no. So I was a manager at the time, so I said to myself, I said, okay, these guys have dispositioned this and said, well, that's because it's rattling around in the flask in transit. Go and simulate transport from the reactor to the site, Chalk River. So they did. So this is in the lab. I'm back to here again. Some things work and some things don't. They're simulating transport of a unirradiated spring from the reactor site to CANDU. As you can see, you can bend it, you can bash the snot out of it, but it doesn't break, as you can see. The irradiated spring, just gently bend it, ping. That's manipulative. That's got to be in the hot cell because these are extremely radioactive. But you can break it with your fingers. That's what that's saying. Not that you'd want to do that. I mean, if you're old enough, maybe you don't care. Give me $1 million, I'll do it. Anyway, and the fracture behavior, the way that these things deform is very different. So when it comes to The unirradiated material, you could still fail it. Who's taken a paperclip and bent it and fatigued it and broken it? Well, you can do that. You can do that. You can get it to fail by cyclic deformation. But this is the irradiated one, and it's got this fracture surface which is faceted. And why it's faceted is because those represent the boundaries of the grain. If you remember back the couple of pictures I showed you where you had a regular structure and then there was this strange kind of boundary structure. Well, this is failing on this boundaries. And this didn't make sense. I remember Stephen, I was working with Stephen at the time, said, aren't the grains supposed to be stronger than everything else? And I said, yes, they are. They normally are. So it shouldn't fail. It shouldn't fail at the boundaries like we have. Except, there's this thing called helium embrittlement. It's been known in the US for many, many years. But for some reason, people here would just go, well, no, I don't want to hear about that. And there was a lot of resistance to even acknowledging that helium was produced. The CANDU reactor is an ideal reactor for producing gobs of helium with nickel because of the spectrum. We have a lot of thermal neutrons in particular. And we have a lot of thermal neutrons because it's designed that way because the fuel is naturally uranium. So you have to beef up the thermal neutron flux in order to keep the reaction going. So why is helium important? Well, here's a couple of pictures of some heavily irradiated material, and this is without helium, and this is with helium. And you notice here, if you look here, it's got a dose here. This has been irradiated with ions, some heavy ions, to 500 dPa. What does that mean? 500 displacements per atom. Every atom in this material has been knocked out of its position 500 times by the time we get to this picture. But the critical bit is the boundary. It's nice and clean. So if you don't have helium, even though you have a lot of damage, the boundary structure can still be nice and clean and stable. But if you have helium around, the helium sticks to the boundary, and that then stabilizes vacancies on the same boundary. So vacancies which form cavities are absorbed actually by the boundaries. So they go into that kind of amorphous mess, that's the boundary, and they jiggle around and they just diffuse away. But when you have helium present, you've perforated something. So just like toilet paper, for those of you who use the washroom, you know that you can tear toilet paper along the perforations, and it tears easily there. So the same thing in a metal, it'll tear easily where you have perforations along the boundary. I was at one meeting with the CNSC and some senior OPG people shortly before I retired, and I was presenting on this, and they're all collectively said, well, can't we just get rid of the helium? Can't we just anneal the material and get rid of it? And the answer was no, but I didn't know how to get this across to them forcefully, because in the CANDU industry, they were still, we don't believe in helium, we're not happy about it. And I wanted to make them damn sure that they understood how critical helium was. And it's a bad actor, not good. So I said to them, no, helium is like herpes. It is forever, you cannot get rid of it. It even has the same acronym or the same abbreviation. So I should have mentioned this, Chris mentioned this to me, he should explain that HE is the shortened version of helium, it's just an abbreviation for helium. But it's also an abbreviation for herpes, so it just keeps it current. So for those of you who have herpes, you'll know what I mean. Apologies for all the messing around at the beginning of the first 2 or 3, 4 or 5 slides, but I hope you've learned something. And hopefully being entertained. That's the most important thing. Oh, we have a question.
These days, we're beginning to hear that everyone is getting excited about fusion now. And maybe after 50 years, it's finally happening. In fission, I get 200 MeV per fission.
Yeah.
I get 2.5 neutrons. So I get 1 neutron for 80 MeV.
Yeah.
In fusion, I'm going to be getting 1 fast neutron every 14.7 MeV.
Yeah.
About 5 times the density. No one has been talking about how much more difficult it's going to be able to keep materials into that kind of an atmosphere. Am I being naive, or
No.
are they just missing something?
It's not an issue north of the border. The Americans expend a huge amount of effort, research effort, on fusion reactors and fusion reactor technology and materials in fusion reactors. So it's just, we're in a cocoon here. You don't see what's going on in the rest of the world. There is a lot of effort on that.
Okay, but I've never seen that issue that it is a potential big problem.
Yeah, and the Americans expend a huge amount of money addressing it. Yeah.
So what is happening with the gather springs? Are they falling apart after 15 years, or is there another fix?
Oh, they reshoot. They tore out all the channels, like in Darlington. They refurbished the whole reactor, all 4 of them. And most of the Bruce reactors don't have those gather springs. There's a few, and it may be life limiting. Brian will agree with this. Often when it comes to reactor lifetime, you're juggling a whole bunch of different things. You know, what is the thing that's going to kill me? Is it pressure tube expansion? Is it the hydride cracking? Is it the garter spring? So in the case of Darlington, they have a limit. So yeah, we know we're on a downward slope here, and we can't trust it. We don't have any confidence that the spaces are going to stay intact for another 5 or 10 years. So we'll refurbish the whole building again. I think that's what they did. They won't tell me that. I don't know that. I'm guessing. But, do they tell you, Brian? I don't know. Nobody tells us anything. We have to guess what's going on. And often, and this is why I like that Diane Kruger thing. It's almost like the story of my life. There's been so many times when I'm just looking outside and seeing what's going on, and seeing meetings and people that are just going the wrong way. And I said, oh, can I talk to you? Can I, look, just give me 5-10 minutes and I can explain why that's not the right thing to do. There's a better thing to do. No, not interested. Often it's an engineering fix. We don't need to understand what's happening with the spaces if we can just tear out the innards and replace it. That's common. Engineering solution for most things in the reactors is just replace it if you can. Oh.
To confirm the analysis of defects, is the microscope a key tool here? Microscope.
No, X-ray diffraction is my favorite. I like X-ray diffraction. I mean, there are a number of different tools. I just showed you the TM because it's a little bit more sexy than showing a peak of an X-ray profile. Oh God, you know, that's very exciting. I mean, I might get excited about it, but nobody else would. But I can show those pictures, which are kind of cool pictures, some of them, you know, and you think, oh yeah, that looks kind of nice. I'd like to do a bit of that myself, you know. And it's great for wallpaper design, so. Anyway, no, but there are other tools, and the microscope on its own is not sufficient. A microscope on its own is not sufficient, but in combination with X-ray diffraction, with other techniques, it's very useful, very powerful.
Tell us about the picture on the front cover of your book.
What's that?
Tell us about the picture on the front cover.
Oh, about the fact that I sent you 5
No.
potential choices, and you said, I like that one. You know.
Well, okay, yeah, but where is that? Yeah.
Oh, that's a PWR in Landshut in Bavaria, Germany. And it wasn't me who came up with that. It's actually in the book somewhere. The jacket design was some English guy. Does it say jacket design? Somewhere. I haven't read this. I mean, I've read a little. No, seriously. You know, like when people, Mark Rogers. I've seen this on TV where you'll get a director and you'll finish a movie, and they say, "Well, tell me about what you've seen it." So I haven't brought myself. I can't look at it. When this arrived, I can't look at it because I'm frightened of all the mistakes that you're going to find. Anyway, yeah, Mark Rogers, he came up with the design. Little bit of to and fro. This part, I can say, yes, I did that bit. You had some comments on the black part here, and I wanted titanium, zirconium, vanadium, iron, chromium there, that part of the periodic table. But I've got to give credit to the jacket designer. He came up with what I thought was a cool design. Good for you, you know.
How long did it take you to put the book together, Malcolm?
2 years. Yeah, one day I got an email from Elsevier, and they said, "Oh, we're soliciting people to write a book. Would you like to write a book?" My first reaction was no. And then after about a week, I said, "You know what? I think I could do that. I think I'd like to do that." And then they said, so you have to put together a proposal. And from that, there's a detailed proposal, but they give you some help. You know, this is what we want to see in the proposal. And then they send that off to an international panel of experts, professors in Japan and France and UK and the US. And they come back and they pull it apart and, you know, criticize the things that you're missing. And one of the things that was missing, in fact, was graphite. I'm assuming it's an English guy, and he said, "You've got nothing on graphite." And so I had to learn a lot about graphite very quickly. So there's 2 chapters. One is on graphite moderated reactors, and the other one is on graphite itself. But it's cool, I learned a lot. That's graphene. You heard of graphene? Graphite is made of stacks of graphene laid on top of one another. And one of the first pioneering pieces of work on graphite was by a lady called Rosalind Franklin. Who knows Rosalind Franklin? Yeah, you know who Rosalind Franklin. She was the archetype, the architect, or she was the, if it wasn't for her, we wouldn't have the double helix. I mean, she did all the preliminary work that allowed them to solve the double helix. But 2 years before she did that, she was working on graphite, you know. So I read her papers and looked at what she was doing, and it was kind of cool, kind of neat, and I learned a bit about graphite. It's really neat, in fact, but I'm coming at it from a different way, different perspective. And I think I had a blinding flash of the obvious in that graphite is orthorhombic. I know, but fortunately there was a guy called Linus Pauling, who's a Nobel Prize winner back in the 60s, a chemist. He'd written a paper about it. And it's obscure, nobody gets to hear about it. But I saw this in somebody's thesis from Texas. And it was just a passing thing, and I thought, oh yeah, that makes sense, you know, like, oh. And like I said, at some point in your life, you know enough about enough things, oh, that's relevant, that's important. And this guy, Linus Pauling, had said, you know what, they're all wrong. Because everybody was saying graphite was hexagonal, it's not. I looked at the diffraction patterns, and they have twofold symmetry. The twofold symmetry is orthorhombic structure. And it actually, everything fell into place then, because there's another form of graphite, which is rhombohedral, what you believe, and you get that from a martensitic transformation, you know. basically that's rhombohedral. You see how it's twisted over? And people have been reporting on this for years. And what I think is the wrong structure, because the hexagonal one, it's kind of like that, where it's like it's not sticking. It's not in a stable position. That's the normal way that people have been reporting graphite for years, and it just doesn't work. It's not logical to have it like that. Orthorhombic definitely works. Rhombohedral definitely works. And the thing is, there was some graphite expert. She sent me an email and said, "Yeah, I think it's because you're coming at it from a different viewpoint. You're actually seeing things that we didn't see. We're accepting the norm. The company line. Graphite is like this. This is how it is. And it takes somebody else to come along and say, that doesn't make sense. And I've been doing research, and I saw this guy said this, and this guy said that. And unlike my Queen student, I didn't think they were irrelevant. I think there was relevant things that you have to pay attention to. And it was great. I mean, I loved it. Painful, but because they only give me 2 years. Because that's when I did the thing, when they said, you've got to talk about graphite. Okay. I don't know anything about graphite, but I will find out. And then they said, now you've got 2 years to do it. I like a challenge. That's it. So you put yourself in that space where, oh my God, I don't think I can do this, but I got to try. And that's the end result. I really appreciate you coming, by the way. I really thank you. Thank you for coming in.